Okay, welcome to Lesson 8. This can be found in your textbook in Section 6.4. So today's lesson, we're going to talk about reaction mechanisms and catalysts. So starting off, we're going to look at elementary reactions. So elementary reactions, each step of a reaction mechanism is called an elementary reaction. Okay, so there are a bunch of reactions that add up to one. So this kind of brings us back to Hess's law. We had a bunch of reactions and we finally get our target equation. So each one of those reactions is called an elementary reaction. Molecules, atoms, ions that are canceled out upon addition of elementary reactions are called reaction intermediates. Okay, so key word here. Anything that is not part of that final, remember that target equation we were looking at with Hess's law? If it is not part of that, then we call that a reaction intermediate. They are essential for the reaction to take place, but are not reactants or products in the overall reaction. For an elementary reaction, the rate law exponents are the same as the stoichiometric coefficients. So before, when we were looking at rate laws before, remember that the rate law exponents m and n, we found them experimentally. We had to do a little work for it. In this case, when we look at elementary reactions, the rate law exponents are the same as the stoichiometric coefficients, right? So if I have, for example, this, when I talk about the stoichiometric coefficients, I'm talking about these numbers in front here. So if I was to write the rate law, remember we only care about the reactants in terms of the rate law. So rate is equal to K times our first reactant. So this time we're going to actually put 2 as our exponent because that's our coefficient in front. And if we look at oxygen, it would have 1. So that would be the rate law for an elementary reaction. Okay, you're going to look at the actual exponents. You don't need to find m and n like we had to do for before. Okay, moving on. Using what we've learned from before, we're going to actually pose and evaluate mechanisms. So is the equations for the elementary steps, one of the things you need to find is that the equations for the elementary steps combine to give that overall equation, and that's where we're talking about Hess's law again. So if we cross everything off on both sides, are we going to get the reaction that we're looking for? 2, is the proposed elementary steps reasonable? The mechanism must support the experiments to determine rate law. So when we look at the rate law that we have up here, so if we look at elementary rate laws, then we have to make sure that it matches the experimental rate law. So the one that we had found the other day with M and N. They have to match up, otherwise it's not a reasonable mechanism. It will make more sense when we do some examples together. One elementary reaction is much slower than the rest, and we call this the rate determining step. Okay, rate determining steps can occur anywhere in a reaction mechanism. Okay, here's my example to help make this a little bit more sense. Okay, so you were chosen to toast bread, and another person was chosen to put the butter on the bread, and you had to make as many buttered toasts as you could over a period of time. So let's go through the steps in order to make that happen. So first we need to start off with our bread. I know I'm an artist. So we have our bread. And how do we make toast? But we put that bread in a toaster. So to that bread, we're going to add some fancy drawings coming here, just so you know. We're going to put it in the toaster. Okay, so if you didn't know, bread plus toaster equals toast. I'm going to put in black, meaning it's burnt toast. Toast. Okay, well, you should try and spell toast right. Then you'd be good to go. So bread plus toaster equals toast. However, this is not the overall reaction that we're looking for. We want buttered toast. So we have to put another reaction. So this would be reaction number 1. And reaction number 2 is we have toast And what do we need to add to that toast now? We need to add some butter. Here. So this is my butter on a plate. So if you have toast and you have butter, what do you think that's going to make? Yeah, that's right. Buttered toast. So this is my butter on my toast. So we have butter toast. So looking at this reaction, we have bread plus toaster is going to give us toast. Our second reaction, we have that toast. Now we can add butter to it, and then we're going to make butter toast. So say you and your best friend in the class, so let's say Johnny and Samantha. Johnny was the one that was making the toast, and Samantha was the one that was buttering it. So let's estimate a time. So how long does it take to make toast? Let's say this takes about 1 minute. And Sam, she's really good at buttering, and that only takes about 10 seconds. So looking at these two reactions, which one of them is actually going to control the amount of butter toast that we can get in the end result? Was it going to be in a reaction number 1, or is it going to be reaction number 2? So obviously, doesn't matter how much butter we have. If we don't have toast to butter, we cannot make buttered toast. So what controls the amount of buttered toast we can make? It's determined by reaction number 1. So this would be considered our rate determining step. So whatever is the slowest one, everything else has to wait on that reaction. Therefore, it is the rate determining step. Okay, so no matter how fast we butter, we cannot butter if there's no toast to butter. Okay, also I want to point out your intermediates. So this is what I was talking about before. Toast is found in both reactions, so that would eventually cancel out. So our overreaction is bread plus a toaster, we get butter and buttered toast. Okay, so toast in this case would be considered an intermediate. So my little example there to help you understand all the different terms a little bit better. Okay, so let's go to an example in a couple of minutes and put all of this terminology and all this evaluating mechanisms into play. Before we do that, though, I'm just going to quickly, you know what, let's go back to catalyst. So let's go and do an example together while it's fresh in our mind. So you should turn to this and have this in front of you. So it says here, consider the reaction between 2-bromo, 2-methylpropane, and water. Rated experiments show that the reaction is first order, so probably important, I would underline first order. First order in 2-bromo, 2-methylpropane. But it is 0 order in water. Demonstrate that the accepted mechanism shown below is reasonable. So just like our toast before, or buttered toast, we had 2 different reactions. So in this one, we have 1, 2, 3 different reactions in order to hit our target equation. This, just like we had for Hess's law, this would be your target equation. Okay, that's our goal. So remember that rate experiment showed the reaction is first order. So first order means that the exponent for this is going to be 1, and 0 order meaning for water it's going to be 0. So let's write the rate law up in the top corner here. So the rate law for the experiment, so our initial rate law would be and remember our exponent is going to be 1 because it says it's the first order. And then we're going to have our second reactant, which is water. And it has the rate law of 0. Hey, if anything has a rate law of 0, it's meaning it's not actually really part of the rate law, so we can actually cross out water. So the rate law for the experiment, so someone did all the mathematical equations like they did before when we had to find m and n, and they're telling us that m is 1 and that n is 0. Okay? So that would be our final rate law for that. So we need to figure out if this is reasonable. 3 things that need to match up in order to consider this to be a reasonable mechanism. So it's basically asking you that if we go through step 1, 2, 3, is it going to give us what we're actually looking for? So the first step that you need to look at is do the steps add up to the overall reaction? So the steps that we have above there, steps 1, 2, 3, RXN stands for reaction. That's a question mark, not a period. Okay, so in order to do this, we need to figure this out. So we have step 1, step 2, step 3. We're going to cross off anything that's the same on both sides. So basically what you're doing here is Hess's law, narrowing it down to get to a reaction that we're looking for. So a little bit of crossing off here. So if we look, we have this on one side, this on the other. We also have this and this. And then we can't cross anything else off. So let's write what's left over to get a final reaction. So we have CH3 CBr, plus we also have water on this side, plus hydrogen ion, and then CH3COH. Okay, so this is, so I'm going to put this. So if we cross everything off and add everything up that's on each side, we want to see that this matches the target equation, right? Remember from above here? So if we look in comparison, oh, I forgot my Br, bromine ion, we'll see that it actually matches up. So do the steps add up to the overall reaction? We would say yes. We're not done there though. We need to ask another question. 2. Are the steps reasonable in terms of their molecularity? And that's referring to the number of particles involved in the elementary reactions. Okay, so what that means is, are the steps reasonable in terms of their molecular number of particles involved in the elementary reaction? So we have something called unimolecular, bimolecular, and trimolecular. So what that means is, if you only have one reactant, the chances of reacting is pretty high. If you have 2 reactants, the chances of them hitting each other at the exact orientation and occurring is usually pretty high. if you have 3 molecules trying to react to make specific products and hitting at the exact same time, at the exact same orientation that works out to become products, is highly unlikely. So if you refer to walking down J. Clark hallways, right? Chances of you making it through the hallway by yourself is pretty good. Chances of you bumping into someone on a regular day in J. Clark, pretty high. Okay, so running into someone, I bet you've done it, you've bumped into someone before. But the chances of actually 3 people bumping into each other at the exact same time in the hallways is pretty slim. So highly unlikely that that would occur. So you're going to look at the amount of molecules on the reactant side and decide whether it's likely that those molecules will react in order to form a product. So if we look at step number 1, we see that we only have 1 reactant. So we call that unimolecular. And if something is unimolecular, good to go. Step 2, we have 2 reactants, so that would be bimolecular. Right, so we have 1, 2, and that would be okay. The chance of those colliding is pretty high. And step number 3, we see again we only have 1 reactant, so we'd call that unimolecular again. So that would be good to go. And this is just a side note here. Anything that's trimolecular, so you have 3 reactants that are going to react together, would not occur. That reaction is highly unlikely that that would occur. So in our situation, in our example, we do not have any trimolecular, so we are good to go. The final question that you need to ask in order to analyze this mechanism is the proposed mechanism consistent with the experimentally determined rate? So remember, back at the beginning of this question, we did our rate for the experiment that was given. So our first order and our 0 order and our water. We want to see that the elementary rate is equal to the original rate that we got from doing experimental calculations. So remember what we learned on the previous page, which one of these steps is going to control the overall rate of the actual reaction, right? And we're going to focus on whatever is the slowest rate, which would be step number 1. So let me write that question out for you, so you can copy that down. So the third question you need to ask is the proposed mechanism consistent with the experimentally determined rate? Done. Okay, so you basically want to say, we're going to set it up like this. You call it rate I, and that's the rate of our initial or experimental work that we did from before, equal to the rate of the reaction. That's basically what we're asking. So let's fill in our rate from above. So we had K to CH3 CBr. And we had that to the exponent 1. Okay, in order to get the rate of the reaction right, we're going to look at that slowest step. And what we learned from the previous page when we were doing our notes, that when we look at elementary steps, we want to write out the rate law, it's going to be equal to the slowest step. And in order to get our exponents, we're going to look at the coefficients in front. So if we're going to write the rate law to this, rate would be equal to, okay, we're going to put in our reactant, CH3. CBR, and then our exponent, we only have 1 as our coefficient in front, so it would be to the 1. So we rewrite that down here. We just got from above. And we see that the rates actually do match. So in that case, we are happy. Okay, so that basically tells us if all 3 of those steps match up, so the steps add up to overreaction, check. We are not trimolecular. We have a unimolecular and a bimolecular and another unimolecular. And if we look at the rate of the equation using M and N that was discovered experimentally, and comparing that to the reaction of the slowest step in the reaction, and we see that those are equal, then we can say that this mechanism, in order to get to the overreaction, is reasonable. So a lot of work for one question, and I promise you will have this on a quiz on your test, and probably high chance will be on your exam. So not something you should kind of be like, wow, that's a lot of work, I don't want to do that. Okay, because I promise you, you will have to do this, or I guess you could just accept a 0. But you're better than that. You don't want to accept a 0. So, let's go back, learn a little bit about catalysts, and then we're done for today's note. Okay. So, catalysts. So, if you want, you could also turn to your textbook right now and go to page 302. I did put a figure on your notes, but there's also a figure in your book. 6.18. You can follow along with that in order to help you with this part. So catalyst. A catalyst is a substance that increases the rate of a chemical reaction without being consumed by the reaction. So we add catalysts in order to make a reaction happen faster. However, the catalyst plays no role in the actual reaction in terms of what the outcome of the product would be. It just speeds up the actual reaction. So they work by lowering the activation energy. So remember, we learned that a couple of classes ago. So we're looking at EA of a reaction so that a larger fraction of the reactants had sufficient energy to react. So remember, if we want a reaction to occur, there are 2 things that have to happen. They have to have the correct orientation when they meet, and they have to have sufficient energy. So what a catalyst does is actually lowers that activation energy so that more reactions can actually take place. They accomplish this by providing an alternative mechanism for the reaction. Catalysts make several industrial reactions economically viable. Enzymes are a biological catalyst. So enormous protein molecules that have a lock and key fit, those of you that may have taken biology already have probably learned about the lock and key method of an enzyme that locks and keys with their substrate. They are involved in many functions of the human body, including digestion and metabolism. So we're going to focus more on the catalyst in order to speed up regular chemical reactions. We're not going to focus too much on enzyme, but do take note that there are biological catalysts that are present in our body. So here is one of those potential energy diagrams again. And it's just showing you what the difference is between an actual catalyst and a reaction without the catalyst. So we've seen these reactions time and time again. So this is an endothermic or an exothermic potential energy diagram. Good, you said exothermic, hopefully. Okay, this would be an exothermic reaction. Okay, energy is being released. So we start out our reactants. I'm gonna pick a different color here. We have our reactants. Okay, we start to gain that energy. We get enough energy to get up to the top of that hill, and then we can produce the products that we're looking for. If we have that catalyst, instead, look at the difference in the amount of energy that is required to produce those products. So instead of the reactants going all the way up there, the reactants only have to get this much energy before they produce the products that are required. So in this case, you'll see that it's lower than it previously would have without the actual catalyst. And that's basically all you need to take away from that, is that it actually is lowered. Here's just a small picture explaining the lock and key method with the substrate. So basically you have a substrate comes into your active site. It has a specific form. When it fits in, it basically kind of locks into that position. You will need to know about the enzyme lock and key for your application questions, which we'll get into that a little bit later. But you'll see it locks in. If the enzyme has the proper lock and binds properly, then a new product is produced, and then they're removed from that key, and they're on their way with the products. Okay, so it's called an active site at the enzyme. And that is it for today's lesson. Okay, I will see you guys later.